and then I'll use that to start. Okay, first of all, 6033 in the news. We are back in space today. Karen, you'll be excited about this one in particular. So one interesting thing that happened recently is that NASA flew a helicopter on Mars, which is super cool. But to make that happen, they had to push a software update to Perseverance on Mars. And this is relevant to 033 for a couple of reasons. One, this was in many ways the topic of last year's design project. So the design projects do come up in the real world. But it's kind of interesting to think about how this happens, right? How do we push software updates to somewhere like Mars? On the one hand, it's kind of interesting from a networking perspective. So you have a piece of software, say sitting at JPL, it has to travel through the deep space network, which is comprised of satellites on Earth and satellites orbiting Mars. And you have all sorts of different constraints in space that you don't have on Earth. For instances, you might send part of that update to one satellite, on Earth, and then it's going to have, it might have a line of sight to a satellite orbiting Mars, and then the satellite goes around the other side of Mars, right? So you have a lot of interesting outages to deal with. It's a pretty interesting networking environment. But we're not talking about networking, right? Well, we're sort of talking about networking today, but since we're also talking about distributed systems, I'm using this event as a segue to talk about an event from 2 years ago, because I talked about this in lecture in 2019, and there's no reason to not talk about it again today. So do any of you all recognize this image? Does anybody remember what is going on in this image? It's okay if not. Yeah, I was gonna say your space knowledge was not a prerequisite to 033. Yeah, so this is the first image, of a black hole, which is really, really, really neat for so many reasons. And the parts that I'll call out for you in 033 are just how this image came together was a huge distributed systems problem. So for one, NASA is collecting data from a bunch of different sites, right? So you can see some of them are at like the South Pole. They're sort of spread all over the globe. And you can read this, this article that I've linked to here tells you sort of all about this system. And I just want to highlight some pieces that relate to what we're doing now. Also, my computer keeps telling me that my internet connection is unstable. So if something happens, I'll come back, don't worry. If something major happens, I'll record a lecture for you, but let's see how far we get. So some choice quotes from this paper. One is just talking about kind of, how they are able to store all of this data. They got so much data to create this image. So it's stored across 32 hard drives, sort of writing slices to different hard drives, all right? Oh yeah, Howie has another 033 news item. That's a news item for a later lecture. A lot happened this weekend related to 033. All right, so they're storing all of this data, and they have to transmit, parts of this data around to the sites. And they mentioned how, this is possible, right? Sending data is possible, but to do it in the way you might want to, you need a really robust internet connection, right? You don't always have that, right? You don't always have that, say, from the South Pole to everywhere else, right? So they're dealing with internet connections, even on Earth, that might not be as robust as they'd like. All of these things involve logs, right? And so these are the style of logs that you've seen in lecture. So all of the setup and verification, they're keeping logs as an archive of what's going on. And indeed, even at NASA, things do fail, right? So you can see a little bit here, they had a hard drive failure, which we talked about in the very first lecture in this part of 033. I am not an expert in this. Part of how they dealt with this is just sort of their system was able to adjust to this. And I think some of the data loss wasn't that important. But yeah, I really, really like to talk about this kind of thing because I think that, we in class, we talk about transactions as like, doing a bank transaction or buying something online. And those are really good examples because we sort of understand them really well. And I can make it really precise exactly the steps that happen there. But these same issues come up on things in space, which is like, oh, guys, space is like so neat. So it's just cool to see how these problems come up in all parts of the world. And I'll call out Howie in the chat again. There was an interesting BGP, event over the weekend. And as always, because I am in charge of O33, I learned about this from multiple people who sent it to me all at roughly the same time as soon as it was kind of came out. So we will definitely, we'll talk a little bit about that later in O33. But what are we doing today? Today, we are moving beyond one machine. All right, so we have been in this world where we're thinking about transactions, right? We're thinking about atomicity and isolation, but we've really been thinking about like doing this all on a single machine failing. All right, so today we're going to start to put some other machines into the mix. All right, and what we're going to try to do is still support atomic transactions even across multiple machines. All right, so there's going to be one protocol that does that for us. The protocol is called two-phase commit. I will explain it to you in a matter of minutes. And a lot of what we're going to try to do today is understand how this protocol behaves under all sorts of different types of failures. All right. But since we're moving to the world of more than one machines, let's just imagine how this might work at first. All right. So suppose that, again, we're going to run a bank. We're transferring money between accounts. But now the bank has gotten big enough that we want to store accounts that say, you know, from people whose names begin with the letters A through M on one machine and then N through Z on another machine. All right. So we're not going to have anything fail. We're just going to see how this works. And the first thing we're going to do, we're just going to transfer money from account A to account B. The reason we're doing that, say we're going to have a client, it only requires one machine, right? Both of these accounts are on a single machine. But in this world where we're going to have more than one server, we'll usually introduce another piece of the system, right? So we'll usually have a coordinator in here, right? And part of the coordinator's job, I mean, it is to coordinate the transactions, and it's going to have an important role as we go on. But for this starting example, it's largely going to help pass messages from the client to the right server. All right. So for instance, the client wants to begin the bank transfer. It'll send that message to the coordinator. The coordinator will take care of alerting the relevant server, hey, this transaction is about to start. All right. That server is, you know, going to respond, right? There's going to be no failures in this. So the server is just going to respond like, okay, I'm sort of ready. Right. And then coordinator says, okay, go ahead. And then we start to do the steps of our transaction. All right. Subtracting amount dollars from account A, adding amount dollars to account B, and then committing the transaction. Right, so if everything goes okay, all of these responses from the server, all of these arrows going back in this direction, they're all just indicating like, yeah, things are going okay. I've done this step. All right. And so really the coordinator is, it's just relaying requests at this point. You can anticipate a few things we will need to deal with once we introduce failures, right? What if messages are lost? If this server fails, how would we detect it, right? And then what should we do? What if the coordinator fails? But at this stage, I think there's, an even, question to deal with first is, well, what's the coordinator doing, right? Why isn't our client maybe just communicating with the A to M server first, right? Well, let's do a different transfer. Let's transfer from account A to account Z. This means we're going to need another server. And then you can maybe start to understand what the coordinator is nice for. The client only has to communicate with the coordinator. Coordinator is going to pass messages to these servers. I'll show you this in a second. Right, so if we on the back end wanted to change how data was laid out, that's something that's kind of contained within the servers and the coordinator, right, within the back end of our system. We wouldn't have to communicate anything to any clients. Right, so it's a nice abstraction to allow clients to only communicate with the coordinator. But there's going to be other stuff as well. So again, we're going to do a bank transfer between A and Z. Nothing's going to fail. I just want you to see how messages are going to flow through this system. Same deal. We're beginning the transaction, right? And the coordinator is going to let the relevant servers know. This time, it's our A to M server, and then also this N to Z server, right? And then the coordinator will tell the client like, okay, go ahead with the next step. Now, first on the slide, I'm drawing all of these communications sort of down in time, right? So in particular, it looks as though I'm saying, okay, send a message to the A to M server, get a response, and then send a message to the N to Z server, get a response. There's no reason that our coordinator couldn't send these messages at the exact same time. You can issue those in parallel. I just want you to be able to see it on the slide here. All right, so doing that, we'll keep going. Subtracting amount dollars from account A, just like before, just a bank transfer. We're going to add amount dollars to account Z. Again, bank transfer. Client's ready to commit the transaction. Again, the coordinator is going to let the two servers know, okay, you could commit. All right, so this is a natural extension of what we were doing before. But now here's the problem. All right, this is not what we are actually going to do in practice, right? Because what if something fails, right? And there are a lot of different things that could fail. You know, imagine I lost a message, right? At this point, our A to M server has committed the transaction, right? It got this message from the coordinator that it would have written a commit record to its log, right? But the N to Z server did not commit the transaction, right? So we have a problem, right? One server committed, the other did not. We don't really know what's up with this transaction. Like, is it all done? Right? We'd have similar problems, you know, if the N to Z server crashed, right? We'd have similar problems with lots of different types of failures. And this is the main issue we have to solve today, right? We have multiple servers involved in a single transaction. They can experience different events, right? One might commit where the other fails. They might receive messages in a different order, all of these things. All right, so our job today is to design a protocol to deal with this. We want atomicity across these servers. So this is known as multi-site atomicity. So like each individual server is a site. All right. Now I've called out a bunch of different types of failures, right? Message loss, message reordering, worker failure. So I'm going to start calling the two servers here workers, coordinator failure. We're going to come to all of that, but you actually know how to deal with the first two, right? Message loss and message reordering, we're going to handle those with a reliable transfer protocol, right? I will show you examples specifically just in case, you know, some of the reliable transport protocol knowledge has left you, right? Which is okay, it happens. But imagine that messages are going to have sequence numbers. There's going to be acts, right? So message loss we can handle, message reordering we can handle. The worker and the coordinator failures, those are the big ones that we're going to have to deal with. All right. And the big question we will have to ask ourselves is, for any particular failure, what does it mean for the transaction, right? Are we at a point, are we past the commit point, in which case we have to get everybody involved to commit the transaction, right? Or are we before the commit point, in which case we can abort the transaction, right? We can stop it, right? So let me show you the protocol that we're going to use. I'm going to show it to you up front first, because I want you to get a sense of sort of what's involved, where the messages are going. And then we're going to look at all of the different failures, right, that can happen. We're going to try to understand how this protocol helps us with all of these failures. All right, so the basic solution is a protocol called two-phase commit, right, where nodes, in some sense, agree that they're ready to commit before they actually commit, right? So two-phase commit, not to be confused with two-phase locking, right? We learned two-phase locking last week. It provides isolation. Two-phase commit is used for multi-site atomicity. They are used for two different problems. They unfortunately sound the same, but they're used for two different problems. All right, so let's see two-phase commit. We're going to assume first all of the parts of the transaction, like before the commit, they've happened, right? If anything failed in the middle, right, we would actually be fine. We'll come to that in a little bit, but assume that we've done all of the, I don't want to say boring parts of the transaction, all of the parts prior to commit, because commit is where things get exciting. All right, so at this point, the client is ready to commit the transaction. Here is what two-phase commit looks like. It looks exactly how it sounds. It has two phases. All right, so the client will send a request to the coordinator to commit. The coordinator is not going to forward along a commit message to these machines. Instead, it's going to forward, we're going to call prepare messages. right? This is going to get these servers, these workers into a prepared state. And you can think of prepared as tentatively committed, right? They will write a, prepare record to the log, right? We'll talk more about that later on, but they are not committed yet, right? They'll respond to the coordinator. Once the coordinator hears from everybody, right? It knows, okay, everybody's prepared. We'll let the client know, okay, things are good. And then it will send commit messages to these servers, right? And they will commit. So here are your two phases. There's the prepare phase and there is the commit phase, right? Prepared, if the workers are prepared, what we want this to mean is that they will definitely commit if the coordinator tells them to commit. All right. And so at this point, you might look at this and say like, okay, I understand how the messages are going. I see that there are two phases, but I don't understand why we need two phases. All right. So that is what I'm going to try to illuminate for you over the next 30 minutes or so. All right. So let's just look at how this protocol deals with certain types of failures. All right. We're going to go through a bunch of different classes of failures. And our general goal will be to ask ourselves the question, are we before or after the commit point? All right, we'll make the commit point a little bit more precise, but the commit point is going to be around here. All right, so after everyone is prepared, but before we're sending commit messages. All right, this is the crux of how we have to handle failures, because if we're before the commit point, it's safe to abort the transaction. If we're after the commit point, everybody's got to get committed no matter what fails. All right, so let's break some things. Let's fail. For now, I'm going to assume that the coordinator is not failing, right? We'll remove that assumption at the end of lecture, right? So don't worry, but just the coordinator is going to stay up for the next 15 minutes or so, right? So let's think about where we might fail. Again, here are all of our, here's all of the early parts of our transaction. If a worker were to fail before we even get to the prepare phase, all right, before any prepared messages have been sent or anything like that, say our N to Z server fails, all right, what can we do, right? We've not reached the commit point. It is safe to abort this transaction. And that's exactly what we'll see. All right, the coordinator will just tell the client, hey, I can't complete this transaction, right? Not all of my workers are online. And you can assume that the coordinator can detect these failures. Imagine that it's running a hello protocol or something like that between itself and the servers, right? It's pinging the servers every second or so, right? It's going to know if one of its servers is down, right? So worker failure before we get to prepare, it's okay to abort, right? We don't have to do anything particularly interesting here. Now, even though we know that message loss can be handled by reliable transport, I just want to show you an example of what this would look like, right? Again, just to refresh your mind about sort of how reliable transport works, right? So let's imagine, again, we've done all of the interesting steps of the transaction. We're ready to commit. Coordinator gets this commit message, and it sends a prepare message to A, but it gets lost, right? Well, the coordinator is waiting for an ACK from A. It's waiting for that response. It's not hearing it. It's going to time out and resend, right? Just like what you would expect with a reliable transport protocol, right? And we can go on sending our prepare messages to the other workers, right? And again, you can send these prepare messages all at once. They can all go out in parallel. They don't have to be in sequence. That's just how I'm drawing them on the slides, right? Now, messages can get lost, so can ACKs, right? So imagine a slightly different scenario. The prepare message to our first worker arrives and the ACK is lost. From the coordinator standpoint, this is just like what we saw with TCP. It didn't get a response. It's going to time out. It's going to resend. But again, we're assuming sequence numbers are here, right? The A to M server, it'll ACK that duplicate request, right? It now got 2 copies of this prepare message, but it doesn't need to reprocess it, right? It's already processed it. We can go on, right? So you could imagine, you could imagine all of this running on top of TCP. That's a fine abstraction. We don't really need all of the stuff that comes along with TCP. We really only need sequence numbers and ACKs. Like we don't need congestion control. We don't need slow start. We don't need all of that stuff. So but we need sequence numbers and ACKs. All right, so this is how message loss would be handled at basically any point in this protocol. So we're not going to go through message failure examples anymore. All right, now let's make things a little bit more interesting. Right, let's have some machines fail. So suppose we're in this middle of this prepared phase. All right, in particular, what we want to see is that one of the servers is prepared. Right, this A to M server, it has prepared. It's written this prepare record to its log. But then the N to Z server fails. All right, what can we do here? Right, have we reached the commit point? That's the question. Right, we haven't reached the commit point. All right, the coordinator has not sent commit messages to any worker. It hasn't sent sort of a message back to the client indicating that the transaction has committed. We're not at a commit point. All right, some of our servers are prepared, not all of them. No one's committed. It's again okay. It's okay to abort this transaction. Right, it's okay to say no, can't go through with it. All right, this other server is down. I can't make it, can't complete it. All right, and in particular, we would want our coordinator, to let the A to M server know that, hey, this transaction is not going to be committed. All right, we don't want the servers to have a lot of unresolved transactions around. So the coordinator will make this explicit, send this explicit message to any live servers that have been prepared. Right, and then it will tell the client, hey, I'm aborting the transaction. Right, so up until this point, the commit point, things are all resolved in essentially the same way. Right, which is that we're giving up on this transaction. All right, it's not committed. We're before the commit point. It's safe to abort. This is fine. Right, our coordinator will let any servers that have prepared to commit know that they're not going to need to. They'll let them know that it's going to abort. But otherwise, there's sort of nothing special to do here. Right, so let's go after the commit point, right? If you remember back in the day, 2 weeks ago or so, maybe 2.5 weeks ago, when we talked about, say, getting shadow copies to work, right? We went down that whole journey together of trying to rename atomic, right? Anything before the commit point, right? We didn't have to do much because it was okay to just say, well, we give up. This isn't working. We've aborted, right? It's not going to happen, right? The problem was that once we'd reached that commit point, we had to make sure everything went through, right? So that's what we're going to do now. So suppose now we're in the commit phase and one of our workers fails, right? What happens, right? What has to happen? We are after the commit point, right? We can't just abort the transaction, right? We can't. That's what atomicity means, right? So how are we going to do this? How are we going to, in recovery, how are we going to make sure workers recover into this prepared state and then commit, right? We've got to get this N to Z server to commit the transaction once it comes back online, all right? This is why when our servers get this prepare message, they're writing a prepare record to the log, right? That's what this record is going to help us do. Because in the part of the recovery process, the N to Z server comes back online, can read through its log, right? And it can say, okay, let me figure out the status of every transaction, right? Which ones are prepared, right? But not committed, right? So as it does that, once it has done that, it's come back online, right? So we're after some point, the N to Z servers come back online. It can ask the coordinator, hey, should I commit this transaction? I had it prepared. I didn't get an explicit abort message. I didn't get a commit message. What should I do? Right? And our coordinator can answer that request. Right? It could answer this in any number of ways. It could certainly just read through its own log and figure out the state. Or it could keep, say, a table mapping sort of, this is the transaction ID, this is its eventual state, all right? Those are all options here, all right? So this brings us to a question. Why do we need the two phases, right? Why do we need two phases to get this to work, right? The overall issue here, and we're going to deal with coordinator failure in a second, right? But the overall issue here is that we want a single entity, the coordinator, to decide when a transaction has committed, to make this decision on its own, right? In a distributed system, it is tricky to get everybody to make a decision and agree on it, right? The coordinator is in charge of this. But that single machine, it might not be able to decide about all of the transactions quickly enough or track all of the state necessarily. So here is a real world example that I like. And it is not a compelling example in these times, but imagine a year from now. You are trying to get together with a group of your friends to go out to dinner, all right? One approach you could take would be to just tell all your friends, we're eating at 6, all right? It's probably not going to work, right? Some of them might not be able to eat dinner at 6, right? This is true even if you could look at their calendars, right? They might have something pending that hasn't made it onto their calendar yet, right? So another way to approach that would be to ask for some sort of tentative commitment, right? Does 6 p.m. work for you, right? Maybe have your friends block off the time on the calendars if it does. Once everyone agrees, now you're at the commit point, right? Everybody can commit the time. If someone during that process comes back and says, hey, I can't do 6 p.m., you can abort the transaction. Presumably you start over since you like your friends. And so there are all sorts of failure modes there. Some of the stuff that when we think about failure, we typically think of a machine failing. There could be other reasons that a machine needs to abort a transaction, right? Maybe you go to take money out of a bank account and machine, the A to M server comes back and says, there's not enough money to do this. You can't go through with this transaction, all right? So this is sort of the idea behind two-phase commit. And now every time you try to schedule something with friends, you'll think of 6033 and you'll think of this protocol for the rest of your life. So you're welcome. All right, so let's make some other things fail. This is going to allow us to be even more precise about where exactly the commit point is. All right, let's have the coordinator fail. This feels big, right? The coordinator is kind of the thing holding this whole process together. All right, so what exactly is it doing here? All right. Once the coordinator has heard a prepare message from everyone, actually, I'll go back so that you can see it. No, backwards. There we go. So that you can see everyone sort of alive and well. Once the coordinator has heard prepare from everyone, right? So once it's, around this time, it's gonna write commit to its own log. That's the commit point. All right, when the coordinator writes that message, right? If it fails before the commit point, it's okay to abort, right? Once the coordinator has heard a commit from everybody, then it's going to write a done record to its log because it can it can remove a lot of maybe lingering state about that transaction. All right, so now that we have that more precisely defined, we could talk about, okay, suppose the coordinator fails during the prepare phase. All right. Just because this is a special failure in the sense that it's, the coordinator failing, sort of the somewhat centralized component of this system, we still have the same question, right? Are we before the commit point or are we after the commit point? All right. If we are in the prepared phase, we're still before the commit point. All right. No one has committed yet. The coordinator has not written that commit record to its log. None of the workers have written a commit record to their log. Once the coordinator comes back online, it's okay to abort this transaction. We're before the commit point. This is okay. All right. And notice, it sent an abort message to the A to M server, which had also gotten a prepared message. The N to Z server hadn't gotten a prepared message. That's fine. That's fine. They could process the logs just fine. All right. No problem there. All right. But of course, what if we're after the commit point? right? So maybe the coordinator has sent a commit message to one of our servers, but not to the other, and the coordinator fails. All right. Well, we're past the commit point, right? The point of no return. Everybody's got to get committed. All right. So once the coordinator comes back online, it's going to blast out those commit messages again to all of these servers, right? All of the servers that were involved in the transaction. That would be part of its recovery process. Right. And it's fine that the 8AM server gets multiple copies of these. It's got reliable transport. It's fine. It's going to be able to check all of this stuff. All right. Now, there is a downside here. All right. And we will address this downside over a few days in 033. Notice that, go backwards. I'm bad at this. All right. Notice that at this point, the 8AM server, it's committed. It's good to go. This NTZ server is up, right? It hasn't failed. It's written this prepare record to its log, and it's kind of stuck, right? It's in this prepared state. It's tentatively committed, like it is ready to commit, but there's nothing that's telling it to commit because this coordinator has failed, right? This is a downside of two-phase commit. It is a blocking protocol. In the sense that if the coordinator is down, we really can't proceed, right? This NTZ server, it has this unresolved transaction, right? It can't resolve it until the coordinator comes back online, right? In which case it'll get a commit message and it'll respond, all right? So let's assess how we feel about this protocol. We feel positively, I hope. Right? Notice a couple of things. After this transaction is totally done, right? So everybody is, we'll get to here. There we go. Everyone has committed, right? Our coordinator, say at this point, it can write this done record to the log. It can forget about any extraneous state about the transaction. For instance, it might be keeping a table that says, okay, here are all of the transaction IDs of transactions that aren't done yet and sort of their current state so that it can quickly respond to any servers. Once the transaction is done, it can forget about it, though of course everything is still on the log. And so really we don't ever forget about anything here, right? So that is one thing to know. Workers, the 8AM server, NTZ server on the other hand, they can't forget the state of the transaction until after they've heard commit or abort from the coordinator, until they've heard a decision that way. This protocol, because there's sort of so much overhead and coordination, sometimes it can be impractical in like a cross-organization setting. So if you imagine servers being like literally owned by multiple organizations or being really, really far apart, this can start to get impractical. And there are other ways, there are sort of application level ways to deal with that. For those of you who like to have some connections to theory, what this protocol is doing is giving us a way for a set of distributed nodes to reach agreement. All right, this agreement is, do I commit a transaction or do I abort the transaction? All right, the guarantee though is that all nodes eventually learn about the outcome, right? There's no guarantee that they learn about the outcome at the same instance, right? Like if nothing else, you can see on the slide here, even in no failures, right? My A2M server got the commit message here. My NTZ server got the commit message here. And in fact, you can never ensure that within a bounded time. It will eventually happen with very high probability. It is known as the two generals paradox. So we're never going to be able to say like, well, we know that by time X, they'll definitely have all committed. There's always really interesting sequences of failures that can happen. All right. Now, this is two-phase commit. All right. And so again, the problem that we're tackling here is we've got to get all of these nodes to agree whether to commit or abort. All right. We want one thing, right? One piece of the system to make that decision. We want this coordinator to make this decision, but it's got to learn from all of the other nodes, sort of whether they are ready to commit or not. All right, but this alone, this picture alone is not enough for us to have the types of robust distributed systems that we want. All right, remember when we talked about the very first lecture on failure, and I told you that one of the ways, like a very common way for us to measure success in this realm, is to think about availability, right? How much of the time is our system up and ready to use, right? Well, I already showed you, right? If the coordinator fails, we can't really progress, right? That is one problem, right? But now, what about even if a worker fails, right? Some of the data is no longer there, right? This seems antithetical to our whole deal here in this section of 033, right? Our whole exciting idea was to replicate data in different places. And in the setup that I've given you, if this A to M server is down, right, we can safely abort the transaction and that's all fine, but we're missing the data, right? You have a sense of how to deal with this, right? Replication. Have 2 A to M servers, right? We could try to run the same two-phase commit protocol and just treat them as 2 workers, right? That's fine. If one fails, users can still get the data from the other one. But then we have a new problem, all right? This new problem, I'm not going to solve for you today in lecture. You're going to talk about it a lot more in recitation tomorrow, right? Because once we replicate data in a distributed system, we have to ask ourselves, okay, at what point should data be visible to a user? Right? Suppose I'm updating data as part of a transaction. Yeah, okay, after the transaction is totally done, it feels like, okay, everybody should be able to see the results of that transaction. But what if the, worker 1 has committed and worker 2 hasn't yet? Right? Is it still okay to be sending requests to worker 2? How do we know? Right? So one possible goal, the word we use for this is the word I have highlighted here on the slide, consistency. Right? There are a lot of different ways to think about keeping data consistent. So one possible goal, one very intense goal, and the goal that we will achieve on Wednesday, we could try to get single copy consistency. Okay? We're going to talk a lot more about this on Wednesday, but I want to introduce it to you now so you can think about it for tomorrow's recitation. Single copy consistency is a property of the externally visible behavior of a replicated system. So it has to do with how users outside of the system see data that's stored on the system, right? When you have single copy consistency, operations appear to execute as if there is only a single copy of the data. You might have multiple copies stored in various servers around the system, but external users will never be able to infer that. Internally, we're going to have to, there might be failures or disagreement, all right? We'll have to mask them, right? From a user's perspective, it's going to look as if there's a single copy, right? But it's so easy for copies of data to become inconsistent, right? There might not even be failures. It could just be that, one has completed a step of a transaction before another, right? That happens all the time, right? So here's the trade-off. Instead of going for single copy consistency, some systems relax their constraints. This is very, very similar to how when we were talking about isolation, I said, okay, in lecture today, we're going to make it appear as if these transactions are running in sequence, that we're doing like transaction 1, then 2, then 3, right? Well, really, we've got them all interleaved all over the place. Single copy consistency, a very strict idea, all right? To everyone else, it's going to look like there's only one copy of the data, right? Or we give up, right? We relax the constraints. For example, the best example you have of this currently is DNS. Well, I don't know, it's a good example. Maybe you have better examples. DNS does not maintain single copy consistency, right? Some server could have a cached copy while another server got a new mapping, right? That happens constantly, right? We base so many exam questions off that premise, all right? For DNS though, it's okay. The people in charge of setting those mappings understand that DNS doesn't have single copy consistency. Maybe we'd say it has eventual consistency, right? We could probably be a little bit more precise, but we'll go with eventual consistency. Eventually, everybody's going to get the right thing, right? The way that they handle that is, okay, if I'm updating my DNS mapping from, MIT.edu used to be hosted at this IP address, now it's at this IP address. Typically, until caches expire, I'll keep both of them up. So anyone directed to the old IP address, it still gets the content, right? Eventually, everybody will be on the new server, right? You can also be smart about how we set the time to live fields for the caches, right? If we want stuff to get out quicker. All right, so the reason I'm bringing this up now is because this is largely the topic of tomorrow's recitation. There are a lot of different ways to relax consistency, right? Neither one of them is like better than another. Like there's nothing that, single copy consistency is in many ways the most strict. It doesn't make it the best. It just makes it the most strict, right? To decide what type of consistency you even want, you have to understand a lot about what your system needs to do, right? And how you might adapt to different levels of consistency, right? So you'll get a chance to talk about that a lot in tomorrow's recitation. And then on Wednesday, we are going to deal with the fact of trying to get single copy consistency. So we're going to live in a world where we're replicating data on more than one machine, and we're still going to try to get all of this to work, right? So here's where I started us at the beginning. I'm going to change this diagram a little bit, right? We're going to think of that big box there as the coordinator. And our lingering problem here is that we aren't replicating data across multiple machines. So the reason I've given these boxes letters now, you should be thinking of them as unique pieces of data, all right? On Wednesday, we're going to be able to fill in the bottom boxes with some replicated data. All right, so that is two-phase commit. And I have noted here on the last slide, it is often abbreviated 2PC. Two-phase locking is abbreviated 2PL. They are not the same. They just look really similar in their acronyms, but they are not the same. So yeah, look, 7 minutes, you get back. I will hang out if there are questions, but if not, I will see you all on Wednesday. We will get single copy consistency, and then we will be done with the fault tolerance part of lectures. And next week, we'll start breaking things in more interesting ways. Is the coordinator just another server? Yeah, it's just a machine. In terms of the way we think about it, like we don't normally think about the coordinator as also storing data, but there's not necessarily any reason that it couldn't.